Now we're going to take a look at our DC load line. So ultimately we have two components that we can look at, our BE junction and our CE junction. So it turns out that our BE junction is going to look just like the load line that we saw for our diode in a previous unit. And so that's kind of to be expected because as we saw earlier, we were treating the BE junction like a forward bias diode. So if you want to refresh on what that looks like, you can see figure 5.23a, which is on page 306 in the textbook, or you can look on page 123 in my lecture notes that are on Canvas. Now, what's more interesting is we want to consider the load line for the CE junction. So consider load line for our collector emitter junction. And so we had looked at that portion of our circuit a couple videos back. And so in general, what we had seen was that our VCE is equal to VCC minus ICRC. So again, this is related to that particular simple circuit with our common emitter configuration. Well, what we're going to want to do is we're going to want to rearrange this equation a little bit, and let me actually write it down here. So we can say that our IC is equal to VCC divided by RC minus VCE divided by RC. And so the reason we want to do this is now we can easily draw this on our plot for our family of IV curves where we have IC as our dependent variable and VCE as our independent variable. So essentially we can think of this as an equation in point slope form, and it's of course a straight line, and we have endpoints with IC equals 0 and VCE equals 0. So IC equals 0, and so if we have IC equals 0, what we're going to end up with is our VCE is equal to VCC, and our other endpoint is going to be if our VCE is equal to 0. And so in that case, we have that our IC is equal to VCC over RC. So as I said, what we want to do ultimately is plot this on our family of curves. So let's see if we have room here, just barely, perfect. So what we can do then is we say we know sort of our two endpoints. So if we consider values that we looked at in the previous circuit, we had a value here, which in general is VCC over RC for the particular values in that circuit. I believe it was VCC of 10 volts, RC of 2K, so that gives us 5 milliamps of current. The other endpoint is going to be over here, and this is our VCC, which is equal to 10 volts in that previous circuit. And again, I'm just using these two endpoint here from sort of our generalized KVL equation. And so again, this is a linear relationship, so what we can do is we can then draw our load line between these 2 points. So we get something that looks like that. Okay, so now we're kind of going to relate this load line back to our family of IV curves. So what we want to keep in mind is that these blue curves correspond to specific values of base current. So for example, we can have IB equals 5 microamps for this bottommost curve. And of course, we also have a curve here that is 0 base current. So this would be when we're cut off. So cut off with IB equals 0. But then as we move up on these blue curves, our IB is increasing. So for example, this one maybe corresponds to 10 microamps, 15 microamps, 20 microamps, 25 microamps. And it's important to keep in mind too that this is a continuum. This isn't discrete levels. So of course we could add in a curve here. Any point in between these ones that I've drawn, we have another base current value, which again is based on our VBB. So our VBB is setting our base current value. Okay, so again, what we can do is for that particular circuit, we can be operating anywhere along that red line. So let's say our circuit can operate anywhere along the red line. And so what we see then is if we have a really low base voltage, VBB, so if our VBB is low, we're going to be starting out down here because we're going to have zero base current. That base emitter junction is not going to be forward biased, and so we're on that point of our curve, that endpoint. As we increase our VBB, so let's come down here and write some of this so it's a little easier to follow. So if our VBB is increasing, then that leads to an increase in base current. And so just from our equations, we know that that should also lead to an increase in collector current. And sure enough, what we see is as we are increasing our base current, so maybe we move to this point where we have 5 microamps. So of course we have increased our collector current above 0, and we have increased our base current as I've already mentioned. Okay, so as we keep increasing that, then we're just moving up and to the left along this red curve until eventually we get to our other endpoint. Sort of theoretically, we're going to see we can't actually reach that. So in the previous example, we were at an operating point of, we had 4 volts for our VCE and 15 microamps for our current. So we were at a point on this 15 microamp curve. So that was our base current, and that corresponded to a VCE voltage of 4 volts. And so we had some specific collector current, I think it was 3 milliamps if I recall. And so this point here, which I've drawn in green, is our Q point, or our quiescent point. And so again, that's something that is going to be important a little bit later on. And so we can keep increasing. For our previous example, we could have kept increasing our VBB. We would have kept on moving up and to the left on this red curve. However, once we get to a certain point, over here where I've just highlighted, increasing VBB no longer increases our base current, no longer increases our collector current. So at some point, VBB up, so increasing our VBB no longer increases our base current. So IB or IC. And so, as you might imagine, we call this region our saturation region. So we've entered the saturation region, or we could say that our device has become saturated. And so as we can see, we keep increasing VBB, but we just stay here at this value. And so there's a corresponding voltage. And so this voltage is going to be called VCE sat, for VCE saturation. And so typical values of that VCE sat are going to be around 0.1 to 0.3 volts. So in our forward active mode, we said we had IC is equal to beta IB. So if we're in our saturation mode or saturation region, so saturation mode, what we have is that our VCE is always going to be equal to VCE sat. And as a consequence of that, and again, typical values are 0.1 volt to 0.3 volts, can vary depending on the device structure. As a consequence of that VCE equal VCE sat, our IC is going to be less than our beta IB. So we don't have a specific unique relationship between IB and IC. We just know that our collector current is going to be less than it would have been in our forward active mode. So sometimes it can be useful to define in our saturation region IC over IB is equal to beta forced. And this beta forced, based on this equation here, is going to be less than our beta from the forward active mode. So I can say beta sub fam. Oftentimes we'll just leave that off though, but just know that that beta is from our forward active mode. So I've sort of have a handout with some tips, and so that comes from page 309 in the textbook. And so these tips are for our DC analysis of when we're analyzing a circuit, how do we tell if we're in this forward active region? And so let me label this up here in our plot. So of course, over here we have our forward active mode or our forward active region. And then over here, we have our saturation region. So without looking at these curves, how can we look at our circuit and just know which region we're in? So if you look on page 309 or in that handout, we'll see some tips, and we're going to go through a couple examples so we get familiar with how to figure out which region we're in and to calculate relevant values.